So yeah, now I'm standing here again and standing in front of you in the evening, probably some food and all of that. What we thought of is like, talks are nice, but it would also be nice to have kind of a quick question round to some of the experts on important topics that concern all of us. And that's why I would like Martin and Sebastian to come up to the stage real quick. Just as a heads up, this is not supposed to be the regular panel that you're used to, so we don't have chairs here. I'm not going to moderate all of that. The idea is we want to talk a little bit about a question of software tech. So one to the left, one to the right. With one mic, I'm going to pass it around between the both of you. I'm going to ask some questions. You'll hopefully quickly answer. No 10-minute monologues, please. Maybe also not 9, also not 8. Let's keep it short. If there are any questions in the audience, first of all, use that tech cloud. By now, you should know how that works to put stuff in there. If there are interesting things in there, we'll try to pick them up. If there are any questions, raise your hand and we'll try to get that in. The topic for the session today is software stacks. And like we've heard that word quite a bit in the past. Provocative question at the beginning. Do we actually need a software stack? Can experimentalists not just run all the stuff themselves?
Well, the experimentalists would use a software stack of some kind, right? The question is, do we need 100 different ones, or can we actually combine them and kind of have abstractions that allow us to put the stuff together?
Fair enough. What's your experience on that?
I think that's possible. Then the compiler would be named Michael, for example, or Susanne or something. So you could do this in a very hard-coded way. It would be very specialized, but I don't know where we would go with such a device then.
Fair enough. So it could be individual people doing their stuff. It could be highly optimized software, of course. But we're all talking about quantum computing here, and it's a very diverse crowd. We've seen this in the survey at the very beginning. How hard can it actually be to get all those people on the table and talk about the same thing and get them to agree on something?
Well, it's not an easy one. We're very interdisciplinary, right? So it takes some time to get together and find the common language, find the common vocabulary. I think meetings like this help with that. I mean, that's necessary to have. To see if there's any hints over here, but I guess not. And so it is difficult, but I think it's necessary, and I think we're getting there. But it requires talking, having conversations like this, and building on it.
So we should be just building a dictionary and put that online for everyone?
Would be a start. So I thought about like, what is a circuit? So I'm a computer scientist, so for me it's a circuit like a collection of gates. For another person, a circuit is really wires and connections. Or for example, what is an algorithm? Some colleagues say, yeah, creating a GSE state. Yeah, but for me perhaps it's a QA or something. So definitely something like this is needed, yeah.
What's your best definition of a circuit?
A circuit is something you put on a board and you put wires in between, right? So that's an electrical engineering answer. But no, I think that's exactly right. How can we find these common definitions? Dictionary, which would be a start, is probably not just, but it would probably be helpful. But I think also we have different understandings of abstractions. We come from classic computing. We know abstractions. We have abstractions, and we can layer this cleanly. I don't think we can do this just yet in quantum computing. And I think we need to get that in order to come into this ecosystem, and I think that's going to be one of the challenges.
I think Robert, you had a question. You wait.
And just also in order to incentivize them, I probably should shut up, but you know, you guys can ask questions as well. And since you talked about the dictionary or glossary, I have very strong opinions about it. I don't think, I don't think they work in this domain yet, because who is to define? Circuit is a good example. My favorite example is logic versus physical qubit. Do we really get to be the community behind a dictionary? So I'm pretty sure if I ask everyone about you, about your interpretation, if I ask 50 people about their interpretation about physical qubit and things like that, I get 100 different answers. I would say it doesn't work, but feel free to disagree.
Yeah, but at least I would know what kind of interpretations would be there. So, okay, I know that circuit is, or people are there that think about circuit as this and this and this and this, so I would learn about this.
So it is a diverse bunch of people in here, and there would be, I guess there would be many different definitions. So, like, quick shout out, how many different definitions do you think would be there for the terms logical and physical qubits? Just quick. Is it 1, is it 2, is it 10?
More than 1, definitely.
Now, I can think of a scenario that happened where it was at least more than 1. I don't know, come on. Is it 10 different interpretations? 3? 42. 42 is all that's the answer to life. Given these
I can just add something. So I think having these definitions, just knowing that they're different, so perhaps doing a Mentimeter, not a dictionary, but a list of Mentimeters for every single topic that we need, right? And then at least we know they're different, and if we figure out there is a difference, then we can start naming it and hopefully come to a conclusion how we named it. I think that's the step that we have to take.
Very quickly, do you see the diversity in all of this as a pro or as a con?
It's a tricky con. So, it's a tricky pro. So it enables something, but you need to go there. So you need to first solve a couple of problems or questions or difficulties or something. But definitely it opens up something.
Yeah, I think I agree with that. It's a tricky pro because we need the diversity at the moment. Otherwise, we're not going to grow. But at some point, we have to stop being more and more diverse and bring us together. The question is, what's the right sweet spot for doing that?
So I guess when we talk about that and bringing people together, we need to find some interfaces that we can agree on. So not everyone can work across the whole stack. That's a tough task. You can't ask of someone. You can't ask the platform experimentalist, the platform builder to be highly knowledgeable in the applications. Where to define the interface, where to draw the lines.
Or perhaps like to get an interface, but using this diversity, I always get pulled out of the comfort zone in a sense. I more often need to not really defend myself, but let's say to really convince someone else. So this is a nice probing, let's say.
Yeah, we need to get these right abstractions so we can do it and we can start hiding things. Right now we said we can't do this really, but it's not just for the quantum stack itself, but we also have the classic stack, and we need to integrate them together, they have to live together. And we have abstractions there, we need to find the matching abstractions, whether they won't be the same, but at least we know what has to fit together. And so I think abstractions are absolutely necessary to get to.
All right. There's a question in the very back.
Yeah,
yes, go ahead.
I have a very basic question. Can you give me the definition of the software stack? Where does it begin, where does it end?
Who's going to dare to?
Sure, the software stack starts at the application, ends at the firmware. It has to be the whole thing, it has to be holistic, and we have to have the right layers in there. But in the end, if you look at the classic side, it really starts at the high-level application through the libraries, compilers, all the way down to the BMC controllers, which run software at this point too, right? And we need to understand this. The only reason why we don't have to deal with this in the classic side is because we found these abstractions and I don't have to worry what a BMC controller does. We need to get here to the same point. So I think it's really everything.
So really, from me typing in my quantum algorithm in my favorite language down to the control electronics instructions on the hardware. Okay.
Yep. Yes. Hopefully even higher to that. Hopefully the future quantum user will not program their quantum circuit, but have some service that does that for them. Just counting on that. So I hope no one will be writing circuits. I've heard this sentiment quite a bit over the last 2 years. The circuit model is the perfect thing to express use cases, probably. Finding good alternatives seems to be hard. If anyone of you has any opinions on that, maybe I've heard Raphael talk a lot about CRISP and stuff like that. So, any opinions on that, maybe? Or there?
Plenty.
I know that you have strong opinions on that topic. So,
no, I think like again, like the problem is with even the naming, right? Like, what do we mean by circuit? What's the definition of circuit? Because like for me, it's like something other people call the pictures in the papers with the big boxes, which with the letter U on it, a circuit. And to me, that's not a circuit, but like the same problem is even with agreeing, right? But like absolutely, like writing the algorithms as you mentioned, right? Like explicitly as like compiled circuit is just crazy. We need to, as was said a couple of times today, I think we need to exploit the structure of those quantum routines, how I like to call them, with subroutines and like a hierarchical structure. So I think that's really, like right now in my head, like having those hierarchical routines and subroutines is a way to go, and it works pretty well for what I've been doing for like describing the algorithms. it doesn't necessarily go all the way down to execution, but I think, well, that's another thing, right? We need to have different representations, different layers.
Thanks for that. Rafael, anything?
Yeah, maybe if I can add, my number one problem with the circuit model is that circuits are fundamentally non-shareable, basically. So if you write a circuit, it is most likely you and only you who can use that circuit. And maybe you can write some nice interfaces around it, but if you actually want to extend that circuit or use it somewhere, then yeah, that doesn't work anymore. And I guess this is something that we basically have to overcome in order to leverage each other's work.
Talking about reproducibility and reusability, how much of a role does open source play in all of this, according to your opinion?
Well, I think there's doing so much research, I think open source plays a large role because you will have to get more people together and kind of start sharing. Otherwise, what you basically talked about was composability, right? And having this, when we decompose, they need to be able to use other people's work and also need to have access to them. I think open source helps. I mean, a lot of stuff will be closed source. I mean, there's just some IP issues and we'll have to deal with that. Some people want to make money with this, I understand that too. But at the end, there will be a strong, if you look at the classic stack, look at the HPC side, most of it is open source at this point, for good reason, and it has worked really well. And people still make money for it, so I'm very hopeful that.
All right, you mentioned open source combined with academia and research. How does academia in all of this actually compete with industry? How to do that, how to accomplish that, how to compete with the resources, the manpower and the womanpower. Is it possible? Is it a completely hopeless dream?
Well, perhaps I want to broaden it a little bit. I mean, academia versus industry is a tricky thing because the academia has a particular role. But there's a gray zone in between, right? There are research centers, there are national labs, there are some like groundworkers and so on, which fill up a really big spread of gaps. And I think those large research institutions have a responsibility to help build up the environment, build up the software system, the ecosystem. And that can then be fed in by academia, that can feed out to industry, but there has to be this middle ground, I think.
What I also like is these hackathons and stuff, so that there is some interactivity and some fun ways to at least compete, but to play around and perhaps to come up with something new that is perhaps better.
Yes, again.
I have another stupid question. What are the main features a good software stack should have, in your opinion, for quantum computing?
Define domain feature.
No, good. What are features a good software stack should have? Should it optimize to the fullest? Should it be easy extendable? I don't know. Should it be easy to understand?
Yes.
Yes.
Yes to all of that, I guess.
Everything of this.
Directly pops up to my head is modularity, but I mean this is not something quantum specific. So your question is good, but it's not like quantum specific. I would just have a look into software engineering principles and just use all of them also here.
Just do that. I mean, in a wishful world, we would have the best software stack that would do everything, that would solve every problem. We would incorporate all the research methods of the world that appear on the archive. We would put them into a machinery and then say, like, hey, okay, this is now the best software stack ever.
But maybe let me follow up, because if everything, yes to everything, and we should have everything, and in a perfect world, probably unrealistic. So what are the priorities then, maybe?
So I just want to get you, so I want to put one priority out and I want to pick up what I said over here. Composability. If a stack is not composable, where I cannot take different modules from different people, from different environments and put them together and make them work together, then the stack cannot grow. So I think composability for modules, of components, is one of the key aspects.
And it also needs to be truly adoptable. So particularly with the Munich quantum software stack, because it's a hybrid, bringing in the classical and quantum together, it needs to be able to follow patterned processes that are recognizable from the various communities. So we don't want to do anything that's too screwy, that causes too much problems, that makes the portability too challenging. We need to make it where it's easy. We learned that painfully with GPUs. right? And the portability and getting them used, and also we don't want to make those sort of mistakes again with making things too unique. We want to follow on the history and the legacy that we already have established and successful software stack compositions.
Matthias again.
Just to follow up on that. Okay, software stacks in the classical Feld thing, and if they are already established, why don't we have it for quantum? What's the major pain point? Good question.
I think just time. I mean, the classic stacks started developing once we had actually an architecture in place in the 40s and 50s, and then we had something to build on. I don't think we're even at that state yet with quantum computing because we don't have a structured architecture yet like we have on the classic systems. So we need that. We develop abstractions and interfaces and layers. We don't have them yet. So I think that's kind of why we're still growing. That's why we need to define them still. But I think that's our task in the end.
Laura, just take it away.
And I guess another component too to be thinking about is that we've had the compute all working together on one computational system. Now we've got things where in the AI space, like next gen AIs and ASICs, that are disaggregated, so they're separated out. They're monolithics that you have to bring together, right? And so there's different things you have to think about. And the quantum systems right now, because it has a great big fridge, it has the QPU here, you can't tightly integrate it on the same substrate, as that you can do with HPC. So you do have to think about things like disaggregated acceleration, which is something that we have, for the QPUs, but we also have it for the ASICs. That's kind of just another paradigm that we have to think about here, right? So there's things that we're dealing with just with the overall evolution of heterogeneous compute, where quantum is being part of it as well. That also causes some of the advancements that we have to figure out.
I really couldn't agree more. The composability, all of this, like designing something that can be plugged together is very, very important because it also ties to defining proper interfaces that we can all agree on. And I see that term on there. There's a frowned upon term by now, I guess. Standardization. Is it too early for standardization? Is it the time for standardizing? Right.
I mean, if we go for composition and modularity, these modules need to speak to each other, let's say. So there needs to be a well-defined interface, let's say. So I would say that in order to plug and play some stuff together, we need some small standardization. I would not agree, I think, for a standardization for one whole thing, but like sub-standardizations of the kind.
I fully agree. I mean, this is not the whole thing, but it's fine to put the spots so we fit together where we need to interact, is define these interfaces and make it lightweight. Not like these big ANSI or IEEE standards, which takes like years to develop, but let's sit together, come up with a spec, have a community drive that, and have these community standards. If you later on see that it has to be an IEEE standard, then we'll turn it into IEEE standard, but I don't think that's what's going to help us short term.
Right, so assuming we have that at some point, is there just one stack to rule them all, or is there many of them still?
There will definitely be many. We see this now, there's many stacks also on the other. I think if we are successfully make this work, there's one set of standardized interfaces to rule them all. If we have that and everything else works together, we can have dozens of stacks as long as they're composable and interoperable.
Everyone agrees with that? Apparently.
Someone disagrees.
I don't know, I agree with that. But you disagree with something else.
No, but I wanted to follow up on the previous question. So I'm definitely on board with the kind of standardization and not going full IEEE standards. But we need to agree on something. But like, what do you think is actually the good mechanism to do that? Because we can sit here in the room, we can talk about let's represent it this way or that way, but then like everyone will go home or to their office, implement something, and then, well, these things will have friction, there will be different implementations. So what's a good mechanism for driving this kind of community-driven standards, if not like, super formal IEEE specification? And at what level of details should we aim at?
I mean, there have been many examples of successful community standards, particularly on the HPC side, and they always started with a core group that had similar interests coming together, writing it down, making it available, going for public comment. It takes time, it takes effort to go out in the community and work it out and make sure that enough people get together and work on this and have a very open discussion also, so not push something through with a 51% vote, right? But make sure that we all agree on that and everybody is represented in that. As long as you keep those principles in mind, then it can be done. But there's a lot of work, and each standard has to have a core group driving it at the end. And that's what we see for some of these standards like MPI, OpenMP, and the HPC world. They have been driven like this for 25, 30 years, but because a group of people worked as volunteers in that area for that long time. And we need that here too. So we need to really pick our battles, pick the interfaces that we care about most, and get a core group together.
And I think maybe to add to that, because it's very dear to my heart, I think open source really plays a big role in all of this. It just gets so much easier to exchange ideas if you can look at what other people are doing, and if you're not trying to interpret that from papers and from tables and papers, but you can actually look at what they're doing and try to not reinvent the wheel. So this is kind of a call for action for everyone. Please, if you can do open source, if there's no IP problems with whatever you're doing, please do it. It helps everyone in the community to get together. Please.
Hi. So if you would have a priority list, let's say top 3, what would you say are kind of the priorities? What needs to be standardized first and which can wait? And I kind of try to follow this discussion about the software stack. I should mention I'm a physicist. For me,
how easy was it to follow? Being honest.
Well,
okay, not being honest.
Right. So my point is kind of it seems like you're talking also about composition of the stack, right? So if it's composed, then it should be kind of consistent of parts. I'm also an elementary part physicist, right? But my point is kind of then these parts kind of some of them might be already ready. Some of them might need more research and more diversification. So if you could kind of rank order, what would you say is kind of the most kind of where you know the best that this will likely not change in the part?
Is that in the back questions or answers to that question?
Questions. Answers.
And
So just talking for Google specifically, we are systematically building our stack from the bottom up. So we started with things that were control pulses, and now we're working on gates, and next we're adding fault tolerance. So we definitely don't worry too much about connecting algorithmic compilers to our hardware at all. It's very much a bottom-up process, systematic. So that's our approach. Grow it from the bottom up.
But which part would need standardization most?
So I will talk about that tomorrow. I'll basically give you an update as to where we're at in terms of building things up.
sounds
and
good.
probably,
So keeping the tension for tomorrow.
Yeah. The main thing is fault tolerance is complicated in ways that perhaps the community doesn't know yet, just because it's complicated, right? You don't talk about logical C-not gates. You don't talk about many things that you're perhaps used to talking in modern 2D fault tolerance. So we'll talk about that tomorrow.
Right, there was a second answer in the back there? Or was it a question?
Question.
Okay, then first to the answers to the priorities. Any priorities on your side?
So yes, you asked for 3, right? So if I would take 3, first of all, I agree, bottom up, the hardware interface is something we probably understand most at this point, probably also not fully yet, but that would be the one interface. The second one, I think the compiler, everybody's developing, the research community compilers, compiler passes, optimization passes, we would like to see those be composable and be pluggable together, and so that only works with an interface. And then the other one, which I probably from as a personal view, but the interface to the resource management, because that's starting to span communities, that's starting to span into the HPC and the resource management communities. We need to interact with other components that exist already, but it's absolutely imperative to get this going, to get efficient systems and work together in hybrid environments. So that standard, I think, would be really important to establish. We can talk again across communities. But we might agree.
I think I would start with like the language to the top, let's say. So what is the input language? Some cousin or I don't know. And the second one goes a bit into a direction like on some standardization of what is good. Like I would like to go into figure of merits of benchmarking. Everything we're doing, are we interested in the, I don't know, estimated success probability or, so what is what we're optimizing for? And there's so many people that have so many thoughts of what is a good quantum computer, and this is what I would like to standardize somehow. What we are doing, we're working on that.
All right, I think that's a good wish list for the future. I see one thing in the middle right there that is very, very big. Let's take one last question in the very back there before we get to that big thing in the middle. Please go ahead.
Sure. So I was just going to ask, I often say that a good programming model helps the user make good choices. So it helps them, encourages them to design performant and correct code. But to what extent do we know what the good choices are at the moment in quantum?
There's an answer here.
So I think on some level there are things that are always good choices, which are whether if you write a program, whether it's easy to write it, easy to understand. And I'm not saying we should optimize for that, but things like if you write something and it looks like absolute garbage and you need to spend 2 weeks studying it to understand what's going on, that's definitely not a good kind of programming model, right? So I think that this expressibility, so if you have a programming model which doesn't support, for example, there was mentioned at some point today, repeat until success. You need to have something that allows you to do some mid-circuit measurements and then to allow for operations like this. So I think this is also something that's important. And there are certain features that are more important to implement right away rather than some can maybe wait for later, etc. But I think these are some important considerations. Yeah. Thanks for that input. I think we're just in time. It's time for beers, shortly at least. Just a quick reminder, this get-together is happening. Oh, you have something ready?
But finish it, and I will show again where I find it.
That is a good idea. So thank you very much, Martin. Thank you very much, Sebastian, for being here. Thanks, everyone.